Today we're working on our objective 5.3 to be able to graph exponential equations. And what we're going to be using is a table of values and also our desmos.com/calculator to look to see how these exponential functions behave. So we know that the parent function for an exponential is f of x equals b to the power of x, where b is any real number greater than 0 except for 1. And so for our first example here, we're going to look at graphing f of x equals 2 to the power of x. So in order to do that, we want to complete our table of values and graph the points to connect them with a smooth curve. Now we know that x is our input values, and we have our table given from -3 to 3, counting by ones. And so if we substitute those values in for the exponents, we should be able to come up with our points. So again, thinking back to what we knew before, if we have something like 2 to the -3rd power, the negative exponent is telling you that it's in the wrong location. It doesn't belong in the numerator, it belongs in the denominator. Therefore, we wrote it as 1 over 2 to the 3rd power. And we know 2 to the 3rd power is 8. Therefore, our final simplified result is 1/8. So we want to do that with the other x values, thinking about substituting them in, what do they mean, and finding their result. So we'll give you a minute to do that, and then we'll check. So again, if we substitute all of those exponents in for x, and we work on simplifying them, we've got 2 to the -2nd, which is 1/4, 2 to the -1st, which is 1/2, 2 to the power of 0, which is 1, 2 to the 1st is 2, 2 to the 2nd is 4, and 2 to the 3rd is 8. So if we plot those points on our graph, what is that going to look like? It appears something like this. So as x increases, do the values of f of x increase, which we call growth, or decrease, called decay? Well, again, as you look to the right of your graph, as x increases, f of x, those outputs, or y values, increase as well. So we would say this is an increasing function. It's exponential growth. So if we grab Desmos and we graph y equals 2 to the power of x, and we zoom in and out to look at the graph closely, the question is, does the graph intersect the x-axis, and how do we know? And so beginning, perhaps your window looked like this, and we're looking to see where it crosses the x-axis, so that's why I have it highlighted in red. And as you zoomed in and out, you saw that it does not intersect the x-axis. It gets very close to it, but it does not touch. So what do we call that? We call that a horizontal asymptote, and that occurs at y equals 0. If it was written in function notation, we'd say f of x equals 0. So again, the outputs for our function get smaller and smaller and smaller, but they'll never have a value of 0. So it will never touch. Now, still looking at that function, we want to know the domain and range. And remember, the domain is the set of all of the input values being used, and the range is the set of all the output values being used. And as you look at your function, there are no restrictions on the input, so we could say that it's from -infinity to +infinity. For the range, I shall say, if you want to write as an inequality, you could say x is greater than -infinity but less than +infinity. For the range, we can see that we have a boundary here. We know we cannot touch 0 nor go past it. So how do we denote that? We're going to have to use a parenthesis with 0, comma +infinity with our parenthesis as well, showing that it's not ending and it's not touching at 0. So now let's take a look at another function. Let's look at f of x equals 1/2 to the power of x. And just like we did before, we're going to substitute the x values in for x, our inputs, and see what outputs occur. So we'll give you a moment to calculate that information. Again, the negative exponents tell you that the items are in the wrong location. So we have 1/2 to the power of -2. That really means that you have 2 to the 2nd power, which is 4. 1/2 to the -1st power really means it's 2 to the 1st, which is 2. 1/2 to the power of 0 is 1. 1/2 to the power of 1 is 1/2. 1/2 to the power of 2 is 1/4. And 1/2 to the power of 3 is 1/8. So if we plot those points again and connect them with a smooth curve, what results? Again, we can see that we have our continuous function. It looks like it's approaching 0 but not touching. So we would say as x increases, y decreases. This is a decreasing function, a decay function. And again, we can see by zooming in and out, it is not touching the x-axis. It will get smaller and smaller and approach that x-axis and output of 0, but it will not touch it. Therefore, again, we have that horizontal asymptote. And we denote that by a dashed horizontal line, showing that boundary. So again, can we write our domain and range? Domain is a set of all the x values being used. So as we look at our graph, we can see there are no restrictions on the x's. So we could write that as negative infinity to positive infinity inside our parentheses, or x is greater than negative infinity or less than positive infinity. Our range, we do have that restriction again, how it cannot touch 0 nor go past it. So we do our parentheses 0, comma, positive infinity parentheses, or we could say y is greater than 0. We can leave it like that, or if we want to throw in the less than positive infinity, you're welcome to add that in as well. How does the domain and range of f of x equal 1/2 to the power of x compared to the domain and range of f of x equaling 2 to the power of x? Well, if we look at both functions, what do we know? Their domains were the same. The range was also the same because they had that same horizontal asymptote at 0. So now on Desmos, take a moment and graph y equals 2 to the power of x and y equals 5 to the power of x. Are these graphs exponential growth or exponential decay functions? And then, once we have that, we want to see which one's growing the quickest and has the rates of change. So let's see here. In blue, I have my graph of 2 to the power of x, and in green, I have my graph of 5 to the power of x. Which one is growing the fastest? Well, that is 5 to the power of x. It's a multiplier of 5 versus 2. And so that would have the largest positive rate of change. Now we want to graph 1/2 to the power of x and 1/5 to the power of x on Desmos. And again, are they exponential growth or decay? And then we're going to look at their rates. So again, 1/2 to the power of x is in blue, 1/5 to the power of x is in green. Which one is decaying the fastest and has the largest negative average rate of change? Well, that's to the 1/2, right? So we're multiplying by 0.5 instead of a multiplier of 0.2, which is your 1/5. Splitting something up into 2 sections versus 5 sections, that section of 2 would be bigger than each section of 5. So again, let's graph f of x equals 8 times 1/2 to the power of x. We can complete the table and plot the points to see what kind of curve results. So again, substituting the values in for x and working them out, we can see when we input 1, we have an output of 4. We input 2, we have an output of 2. Input 3, output of 1. Input of 4, output of 1/2. What does that graph look like? It looks like so. And here we would classify this as an exponential decay, a decreasing function. Well, keeping that one in mind and thinking back to what the graph of y equals 1/2 to the power of x looks like, what do you notice about the y-intercepts for the graphs? We'll give you a moment to make sure you're looking at those two functions on Desmos to compare the y-intercepts. If you look, the graph of 1/2 to the power of x is a y-intercept at 0, 1, and the graph of y equals 8 times 1/2 to the power of x has a y-intercept at 0, 8. Now, do you have any clues about the functions that might tie you into the y-intercepts? If you notice, the y-intercept is related to the a value, the multiplier. And so your first function, 1/2 to the power of x, technically has a multiplier of 1, an a value of 1. And notice how there's your y-intercept, 0, 1. And then your second function, 8 times to the 1/2 power of x. Remember, here's your a value, multiplier of 8. Notice how there's your y-intercept at 0, 8. So what are some of the key things that we've learned from today? When we talk about our exponential functions, they could either be growth or decay, like we've talked about before. If your multiplier b is greater than 1, it's growth, increasing. If it's between 0 and 1, it's decay, decreasing. We also know that the a value can determine the y-intercept for the graph. So we're going to look to see if you have a multiplier in front of your rate, and that will influence your y-intercept. Okay. We also know that the domain and range are the same for your exponential functions right now. So we've got our domain being from -infinity to +infinity, and our range 0 to +infinity, 0 not being included. We also know that there's a horizontal asymptote as f of x equals 0 because it's in function notation. If it was y, then y equals 0. We know the functions approach 0, their outputs get closer and closer to it, but it will not touch, and that's what that asymptote is telling us. So now you're going to be doing some more practice problems today, identifying based on the equation if it's an exponential growth or decay function or neither. If you're given a graph, can you identify key features like y-intercepts, domain, range, and asymptote? And then can you correctly graph some exponential functions?